Two-dimensional finite element analysis plays an important role in many design scenarios. This video is intended to show analysis of plane stress problem using finite element method. It is expected that audience is familiar with at least basic theory of strength of materials and basic finite element terminology. Consider a two-dimensional planar body is subjected to loading. The main types of loads acting on body are, body force, which is distributed force per unit volume, second is traction, which is a surface load, and third is point load. In two-dimensional problems, displacement at any point is function of x and y. And hence all derived quantities are also function of x and y. The stress and strain components are also clearly shown here. The body force and traction can also be resolved in two components. The stress-strain matrix for plane stress and plane strain conditions are represented like this. Consider a domain subdivided into 10 triangular elements, each having 3 local nodes. Here one such triangular element is shown with its 6 local degrees of freedom. To understand more specifically, the figure shows a rectangular plate divided with 2 triangular elements. The global and local node numbering is also shown here. Nij represents local node number j of element I. This table shows relation between global and local node numbering. It is called element associativity table. The nodes encircled with blue ink are local nodes, and the numbers underlined with red ink are global node numbers. The figure shows one triangular element. An interior point P divides this triangle into 3 distinct triangles. The shape functions n1, n2, n3 in terms of area coordinates are shown mathematically. Graphically they are shown by figure A, figure B and figure C respectively. Since shape functions are linear, this element is called constant strain triangular element. Further, we use isoparametric transformations to represent these shape functions in natural coordinates. Equations 1 and 2 relates the displacement of any interior point, with nodal values of displacement. Equations 3 and 4 relates the coordinates of any interior point, with nodal coordinates. Using notation xi minus xj is equal to xij, we can rewrite these equations as shown by equations 5 and 6. Block A shows u and v are functions of x and y, which are in turn functions of zeta and eta. Block B shows the relation between partial differentials. Block C shows this relation in matrix form. It also shows the Jacobian matrix, J. It is interesting to note that determinant of this Jacobian matrix, J, is twice the area of CST element. Block G shows inverse of Jacobian matrix J, which can be obtained considering relations shown in block F and D. Equations A and B are easily verified. Equation 1 shows the strain vector for two-dimensional conditions, which is further modified by rewriting as in equation 2. Finally, we get strain displacement matrix, B, as shown in equation 3. The elemental stiffness matrix, Ke, can easily be obtained, once you get strain displacement matrix B. The body force term obtained here shows that 1/3 of total body force goes to each node. Consider any edge L12, subjected to traction, which varies uniformly from P1 to P2 as seen in figure A. The component distribution Tx and Ty is shown in figure B and C respectively. After calculating angle theta from geometry, proper signs must be taken into account for finding values of Tx1, Tx2, Ty1 and Ty2. From traction load vector, it can be easily seen that traction is converted into point loads at nodes of a given edge. Now we will proceed for plane stress problem using constant strain triangular element. For the given problem, you have to find elemental stresses, using two-element approximations. First, we will divide the problems into two CST elements and prepare element associativity table, to link local and global degrees of freedom. Strain displacement matrices, B1 and B2 and stress strain matrix, D for plane stress are then calculated. Elemental stiffness matrices are then calculated for two elements. If we use elimination approach, looking at boundary conditions, rows and columns corresponding to first, second, seventh and eighth degree of freedom will be cancelled from global stiffness matrix. Hence reduced matrix will be 4x4 matrix with degrees of freedom 3, 4, 5 and 6 appearing in it only. Here we can see both stiffness matrices K1 and K2. Also, we can see common degrees of freedom shared by them. These are encircled with red ink. Thus, reduced matrix and traction vector are calculated. Using FEM equation we can find out displacement vector Q. Stresses in element, sigma 1 and sigma 2, can be found out using equation D into B into Q, where Q is matrix representing degrees of freedom associated with that particular element. Here you should use element associativity table, to find correct degree of freedom for Q matrix.